The attack begins. The gamma rays scatter electrons in the air, spawning currents that short-circuit electrical infrastructure. Within seconds, power grids and communication networks fail catastrophically across entire continents. This is no sci-fi scenario. The EMP from a gamma ray bomb could plunge modern civilization into chaos by permanently frying complex electronics. And that's just one potential use of weaponized isomers. Theoretical projections of isomer weapons seem torn from science fiction. Neutron beams inducing nuclear reactions, microbombs dwarfing conventional explosives, EMP devices frying electronics silently. The sheer devastation defies belief. These vivid Gedanken experiments illustrate the perils of militarized physics, yet between vision and reality lies a gaping chasm. Despite the apocalyptic scenarios, realizing even one such device remains distant. Producing a weaponizable isomer in any meaningful quantity appears impractical. Even if synthesized, efficient triggering methods are likely decades away, if possible at all. Significant barriers across production, stability, and controlled initiation must fall before the direst threats materialize. Still, we can't ignore the hazards and the threats looming in the shadows. Illicit trafficking of materials, loose radiological sources, and rogue experimentation merit a continued watchful eye to deny access to the malicious-minded. Nuclear isomers are exotic forms of matter that could revolutionize energy production or unleash unbelievable destruction. These intriguing atomic species are like revved-up versions of regular isotopes, packing huge amounts of potential power into an unstable state. So why should we be concerned about nuclear isomers if they're so impractical? In most stable atoms, nucleons, protons, and neutrons pair up neatly. But some nuclei can get excited when one or more nucleons shift into higher energy configurations. Picture an atomic nucleus where neutrons or protons have spun into new orbits, like electrons jumping between shells. These amped up atoms are nuclear isomers. Their energized nucleons can remain trapped in high spin states for years. In effect, isomers act like charged batteries where the nucleons want to drop back to their ground state, releasing floods of gamma radiation in the process. But what if we could trigger that cascade on demand? In the late 1990s, maverick physicists like Carl Collins at the University of Texas claimed that he could unleash energy from hafnium isomers using simple X-ray machines. Collins claimed that irradiating hafnium-178m2 released 60 times more energy than the triggering X-rays. So if that is true, just a fingernail's worth of hafnium might yield TNT's explosive power. You can imagine why the Pentagon took interest. Agencies like DARPA launched classified programs to study isomer triggering. Their goal? Exotic new physics projects directed towards energy weapons, ultra-dense explosives, or EMP devices to fry electronics without fallout. With potential applications ranging from satellite power sources to nuclear grenades, isomers seemed like a strategic jackpot. The startling claims around triggering energy from hafnium isomers remain mired in uncertainty even decades later. Despite tantalizing initial reports, independent efforts to replicate those results have failed. Using state-of-the-art accelerators, multiple teams obtained null observations inconsistent with Collins's initial reports. Reproducing Collins's X-ray tests just wasn't happening. Maybe there were measurement errors given the complexities of working with exotic nuclear states and faint radiation signatures. But branding Collins an outright fraud isn't entirely out of the question because lucrative military funding was involved. Regardless of motives, the consensus today regards the original finding as artifacts rather than breakthroughs. Still, even absent concrete progress, the allure of weaponized isomers continues. Imaginations run wild with the notion of pure fusion bombs beyond fission's reach, particle beams inducing antimatter annihilation, and pinhead-sized explosives dwarfing conventional TNT. But between fantastical projections and physical realities lies a yawning gulf. For all their conceptual appeal, we currently lack the means to practically generate weaponizable isomers, let alone deploy them effectively, and the fundamentals of controlled triggering remain elusive. We are far from unleashing their potential on command. Yet, rather than wholly dispel such scenarios, we would be wise to analyze them with a critical mind. Speculation helps to clarify objectives to work towards or those to assiduously avoid. Creativity excels with discipline, guiding progress and conscience. Even the wildest theory just might catalyze into something unanticipated, yielding amazing results. While isomers provoke both promise and controversy as potential weapons, their peaceful applications also deserve equal attention. Rather than fission bombs or blinding gamma rays, could these unusual atoms one day diagnose or treat medical diseases like cancer? Or maybe power deep space probes to expand our understanding of the universe? The answer? Yes. Even small quantities of hafnium isomers unleash hordes of radiation, but with careful tuning, these gamma and X-ray streams might enable novel imaging techniques to identify medical conditions and even guide treatment. Early detection and treatment of cancerous tumors is just one possibility. Isomers also provide concentrated on-demand energy release. That intrinsic property could fuel miniature power sources, outperforming conventional nuclear batteries. Imagine a spacecraft traveling to the far reaches of the solar system with a reliable isomer generator without the need to refuel, or at least few and far between. They could power satellites or even robotic explorers, digging into alien soils many light years away. What do you think? What other elements need more study that might be able to change life for humankind as we know it? But you can bet your bottom dollar that weaponizing hafnium isomers was intensely studied. As recent as the early 2000s, there was interest in weaponizing hafnium isomers. The idea was that gamma rays emitted by the decaying isomer could be used to kill or incapacitate its target. But there are a number of problems with this idea. First, the energy density of hafnium isomers is relatively low, which means that a large amount of hafnium isomer is needed to make a weapon that is small and portable enough to be practical in any sense. In other words, it's possible, but it would have to be really big. The exact size of a weapon using hafnium depends on a couple of factors, like the desired power yield and the efficiency of the shielding, because remember, these babies are nuclear. A hafnium-packed weapon with a yield of 1 kiloton needs about 100 kilograms of hafnium. For comparison, a nuclear bomb with a yield also of 1 kiloton requires only about 2 kilograms of plutonium or uranium. So a hafnium isomer weapon would have to be about 50 times larger than a nuclear bomb of the same yield. So based on these figures, a hafnium bomb would have to be about the size of a semi-truck or even a small building. Not really practical. Then there's the gamma rays emitted by hafnium isomers, which are very penetrating. That makes them extremely difficult to shield from the radiation, and they would create a massive risk to anyone working with them. Considering all of these factors, the efficiency of the energy produced from hafnium isomers is about 1%. Whereas plutonium or uranium is about 20%, and you need a heck of a lot more hafnium to make it work. The mysteries of these atomic nuclei are still slowly unfolding. Perhaps one day there will be a viable use for them. If money grew on trees, I'd love to see what a new generation of scientists could discover if freed to follow their passions. Perhaps they would uncover isomer secrets, hinting at new realms of physics like Einstein realizing that time slows at high speeds. Rather than fueling destruction, maybe hafnium isomers could energize creative innovations that save lives instead of sending them. The same physics that could power the holy hand grenade could also empower medical implants to monitor health and selectively destroy tumors with surgical precision. Miniaturized isomer devices could be implanted to deliver highly targeted doses of radiation to cancer cells, while avoiding damage to surrounding tissue. We could fight disease by harnessing atomic abilities, rather than unleashing atomic horrors. Beyond fighting cancer, micro-isomer power sources could enable all kinds of medical marvels. Imagine swarms of microbots powered by isomers, patrolling our bloodstream, filtering toxins and keeping cancerous cells in check, or even your cholesterol. Or what about isomer-charged brain implants fine-tuned to monitor neural activity and stimulate specific regions, helping to restore motor skills after trauma or disease? We've only just begun to scratch the surface of the potential healing applications of these bad boys. The mere act of discovery also has value. Pushing the boundaries of knowledge is a fundamental human pursuit that lifts our species. Even if practical applications are proving elusive, unraveling the secrets of hafnium isomers expands our understanding of the quantum realm. Pure science need not be justified by practical spin-offs. The act of exploration is worthwhile itself. Though the road is long, the journey of discovery will continue. Of course, we can't force nature's secrets from her grasp. The truth emerges in its own time. But the human impulse to learn is unstoppable. Whether masters or students, we will keep searching. We will keep trying new approaches and asking new questions. Thanks for watching.